Hello, I welcome you all to this another interesting screencast where we're going to be solving this engineering mechanics problem, and it reads locate the centroid y bar over the composite area, then determine the moment of inertia of this area about the centroidal x prime axis as well as the centroidal y axis. Right. This problem is coming from the Engineering Mechanics Statics textbook, 13th edition by R.C. Hibbeler. So here we are being asked to find centroid. If you remember, we've dealt with centroid and I've done some videos on centroid. And centroid is just a geometric center. Okay, we can think of a point within, if it is a centroid of an area, you can think of a point where all the area is concentrated. Okay, and if the material is homogeneous, you expect the centroid to coincide with the center of mass. It can also coincide with the center of gravity within a uniform gravitational field. And we have also moment of inertia, which we are dealing with, which is moment of inertia of an area, also called area moment of inertia or second moment of area. This is also a geometric property, but a little bit different from centroid. For moment of inertia of an area, this is a geometric property of a shape or an area, such as the cross-section of a beam, which describes how the area is distributed around an axis. An axis where we want to find the moment of inertia of an area. So we can have moment of inertia about the centroidal axis or any other axis that we choose. Mathematically, moment of inertia, or first I start with centroid. For centroid, okay, centroid about the y bar, which is the centroid along the y-axis, which is y bar. So for centroid, this is equal to if for a body like this one, which is a composite body, or I just give a general formula, right? This is equal to integral of y cubed, right, dA divided by dA. Okay, so this is the centroid of a body in the x-axis, and in the in the y-axis. This one is in the y-axis, y bar, and then in the x-axis we have x bar equal to integral of x cubed. X, that is the local centroidal axis of that particular element, okay, within an area. So integral x cubed dA divided by the total area. So this is centroid, okay, centroid of an area. Okay, and then for moment of inertia about the x-axis, we'll have I sub x equal to integral of y squared dA, and moment of inertia about the y-axis is I sub y equals integral of x squared dA. All right. So basically, these are the formulas that we're going to use for finding centroid y bar along the y-axis. We're going to use this formula, and then for finding moment of inertia, we'll use these formulas, but not integrating per se. Instead, we are going to be summing up the moments. So we are going to use the parallel axis theorem. So we'll have, for moment of inertia about the x-axis, we'll have I sub x is equal to centroidal moment of inertia, okay, plus dy squared. This is the distance from a given area to the axis where we want to find the moment of inertia. So dy squared times the area. This is moment of inertia about the x-axis. This is parallel axis theorem. And then moment of inertia about the y-axis is I sub y equal to centroid axis, centroid moment of inertia of an area about the y-axis, which is IYC, then plus dx squared area. So use these two formulas for working out this particular problem. All right, I guess we are done about this explanation. Let's start doing the work. Okay, great. So this is a composite body, like I said, and we have a hole. We've seen this square hole here. Okay, so we also consider it as the shape, but we'll give it a negative area. Okay, and we also give it for finding a centroid to give it negative area, and for finding a moment of inertia we are going to give it negative moment of inertia to say we need to subtract it. So let's give this particular body or composite body the geometric property. We assign it the geometric property. Mind you, the first thing is to find the centroid y bar. Okay, that's the centroid along the y-axis. So let's give it the geometric property that will enable us find that. To start with, let's define the shapes that we have quickly. So for me, I'm going to define three shapes. I have a semicircle. Which is this one here. All right. And then I have so I have this rectangle. Okay, then I have another rectangle, a smaller one, which is a hole, this one in red. Okay, and then I have this semicircle there, this one that I'm outlining in green. All right, the one I'm outlining in green. Okay, of radius 3. So I have basically three shapes. So my first biggest rectangle, I'll assign it my shape number 1. Okay, and then this smaller rectangle, which is basically a hole, some space, a hole like this. Okay, or some space through this composite area. Okay, I'll assign that as my my second shape or second part, and then the semicircle will be my third one. So I've assigned everything that I have. So let me now assign the geometric properties. I'm going to start with shape number 1. So its height is 5. So let's say we want to find the local y curl, that is the centroidal location of each shape with respect to the x-axis. Okay, that's our first step. So let's say we do this like this. I want to minimize the use of space. Okay, we say somewhere there like this. And then our second shape. So let's assume this is the centroid, this point here. Let me mark the centroid. This is the centroid of this part here. This one here in red. This is for shape number 1. And then for shape number 2, let's imagine it is this one there. And then for shape number 3, let's imagine it is somewhere here. Okay, these are just imaginary. So then for shape number 2, let's draw our line. Is going to be somewhere there, to pass somewhere there. Need to use black. Somewhere there. Okay, let's say to pass somewhere there, like so. And then the third shape, let's say to pass somewhere there, like so. Okay, great. This is about it, right? For now, this is about it. We'll get back again when there is need. Let me just work on this so that my space is not littered with a lot of lines. Okay, great, something like that. So there we go. That one there, that one there, that one there. Let's start naming them. So this one here, this one we are calling it as our y, our y1. Okay, y curled y curled 1, which is equal to the height of this rectangle is 5, so it is half of 5, which is just equal to 2.5. Okay, and then this one is y curled of 2. What's y curled of 2? There is an initial distance from the x-axis, which is a 2, plus half of, what's the height of this? The height of this is 5 minus 2, so this is a 3, and then this width, what is the width of this? So this one is what's the width of this one? Let me just write it properly. This one is 3 inches, of course. And then this one, we have 1 on the side, 1 and 1 the other side, and the whole length is 3 plus 3, which is 6. The length here, this is 6, right? So 6 minus 1 and minus 1, right? So 6 minus 1 minus 1, what does it give us? It gives us a 4. Okay, that's a 4 inch. Okay, so there we go. So okay, y curled 2 equal to 2 plus half of 3. Okay, and half of 3 is 1.5. 1.5 plus 2 is a 3.5 inches. And then finally, we have this is a y curled of 3, which is equal to the initial length from the x-axis is a 5, and plus the centroid for a semicircle is 4r divided by 3 pi. This therefore gives us a 5 plus 4, then r is 3 divided by 3 pi. Therefore, y curled 3 is going to be equal to a 5 plus 4 divided by pi. Right? Great. I think we have everything that we need right now. Do we? Yes, we do have everything that we need. Great. So what we need to do now is to find the area. Okay? We need to find the area for each shape. So area 1 is equal to L times B, which is just equal to a 6 times 5, which gives us a 30 inches squared. Area 2 is a 4L times B, which is just equal to a 4 times 3, and this is equal to 12. And area 3 is equal to half of a circle, which is half pi r squared, which is just equal to half by pi, half times pi times 3 squared, and this gives us 3 squared is 9, half of 9 is 4.5 pi. Okay, so now let's find the centroidal moment of inertia. Alright, a moment of inertia I sub x1 is equal to, that is for a rectangle, that's 1 over 12 bh cubed. This is equal to 1 over 12. Our b is 6. This is with respect to the x-axis, okay? So our height is 5 cubed. And if we were to calculate that, so 5 cubed times 6 divided by 12, this gives us a 62.5 inches to the power 4. Moment of inertia, centroidal moment of inertia for part number 2, which is also a rectangle, so this is going to be equal to 1 over 12 bh cubed is equal to, what is this one equal to? This one is equal to 1 over 12. Our b is 4 and our h is 3 cubed. So if we do a calculation, 3 cubed by 4 divided by 12, we have a 9. And then finally, moment of inertia for shape number 3, centroidal, this is half a circle, so it's 1 over 8 pi r to the power 4. Okay, then this is equal to 1 over 8 pi. Our r is 3 to the power 4. This gives us 3 to the power 4 divided by 8. 3 to the power 4 divided by 8. So we have a 10.125 pi. Okay. Let me just create a boundary here. So let's find moment of inertia about the y-axis, centroidal of course, because we are dealing with moment of inertia about the x prime as well as moment of inertia about the y-axis. Okay, IY1, of course, this is a rectangle, so it's 1 over 12 bh cubed. This is equal to 1 over 12. Our b this time around becomes 5 and our h becomes 6 cubed. Then when we calculate this, 6 cubed by 5 divided by 12, this becomes a 90, right? Then moment of inertia for shape number 2, which is also a rectangle, is 1 over 12 bh cubed equal to 1 over 12. Our b this time around for this one becomes a 3. Our height becomes a 4 cubed. Then this one, 4 cubed, this is a cubed there, okay? 4 cubed times 3 divided by 12. This becomes 16, okay? Then finally, moment of inertia for shape number 3, which is equal to moment of inertia, which is equal to Ix3. These are the same. So we have the same value, which is just 10.125 pi. Okay. So let's work out now the we work out which one do we start with. Okay, let's start with centroidal y bar. There we go. I think this is good enough. So we have part, then we have y curled, then we have area, then we have y curled area. Okay, so 1, 2, 3 summation. So for the first one, y curled, what do we have? For the first one, we said it's a 2.5. Second one, it is 5 plus 4 divided by pi. The third one is the second one is 3.5, right? 3.5. Third one is the one that is 5 plus 4 divided by pi. Okay, then the area we found, area 1 is 13, the second one is 12, the third one is 4.5 pi. Then the product, we have 2.5 by 13, 2.5 by 13. This gives us a 75. Okay, and then 3.5 by 12. It gives us, let's not forget to say this area for part number 2 is minus. So area 3.5 by minus 12 is a minus 42. Okay, and then finally 5 plus 4 divided by pi times 4.5 pi. So this gives us 88.6858. Okay, so there we go. Let's add up the area. So 30 minus 12 plus 4.5 pi. This gives us a 32.1372. Then we add up the other product there, 75 minus 42 plus 88.6858. So this gives us a 121.6858. Okay, then y bar therefore, let me write it in blue. Y bar therefore is equal to the summation of y curled area divided by summation of area, which is equal to 121.6858 divided by 32.1372. So this gives us 1372. So this gives us 3.786, 3.79 inches. All right. So this is the final solution for the y bar. So we found what y bar is. So y bar is equal to 3.79. So since we know what y bar is, we need to find centroidal moment of inertia about x prime. So we know y bar, but we need to find those distances now, new distances from those particular area to the centroidal to x prime. So we have this height here. We have this one, we found it as 3.79. okay, So this is equal to 3.79. Okay. Let me rub this line. This line, we can turn it like this here. Alright. So this is 3.79 inches. Okay. So now let's find the new distances. I'll use red. These new distances that we are looking for us to find moment of inertia about the x prime axis, we need to find this distance here. This one here. Okay, this is the one we are looking for. For there, we are looking for, no, not that one there. Sorry. We are looking for that distance there. Okay. And then there we are looking for this distance here. And then there we are looking for this distance here. Okay. So these are the distances we are looking for. I'll use blue this time around. So these distances, this distance there and that distance there. So let's start with the first one. So this distance, we'll call it y prime. Let's call them y prime caret 1. Okay, it's going to be equal to y bar, the length of y bar, which is 3.79 minus 3.7 minus the length of the centroidal distance y1. So this one basically is equal to, let me write the expression, it's equal to y1 caret minus, y bar minus y1 caret. Okay, which is equal to 3.79 minus 2.5. Okay, and this is equal to, what is that one equal to? 3.79 minus 2.5 is equal to 1.29. Okay, those are the distances we are looking for. Alright, and then this one here, let me use green for this one. This one here, okay, so this one is y caret prime 2, which is also equal to y1 bar, y2, y bar, this is just y bar, okay, it's not 1, this is just y bar. This is y bar minus y caret 2, which is equal to, where is it? Why is y2? This is equal to 3.79 minus 3.5. This is equal to 3.79 minus 3.5. This is equal to 0.29. Okay. And then finally, we have this one. So this one is y prime caret 3, which is equal to y bar minus y3 caret, which is equal to, so the other one is bigger instead, but we're interested in the modulus, y3 caret minus y bar, which is equal to, because it's bigger the other one, 5 plus 4 over pi minus 3.79. This therefore is equal to, let me create a boundary here. This therefore is equal to, so 5 minus 3.79. So this just becomes a 1. This becomes a 1.21 plus 4 divided by pi. So we have all the information that we need. This information will help us to fill in another table that we want to prepare. Alright, so let's prepare another table that will help us find moment of inertia about x prime. Let's fill the table. So we have part 1. We have part 1. We have part 1, 2, and 3. And then we have summation. Then moment of inertia, we said about the x-axis. Centroidal for part 1 is a 62.5. The second one was 9. Mind you, it has to be negative, don't forget. The third one we said is a 10.1. It's a 10.125 pi. Alright. And then we have the centroidal y prime distances. These are the new distances. So the first one is a 1.29. This is with reference from the x prime. So each shape is distance from the x prime axis. Okay. So this, we found it after finding the centroidal distance of this composite. And then later on, now we want to find moment of inertia about the x prime axis. Okay. So 1.29. Then the second one is 0.29. Then the third one is a 1.21 plus 4 divided by pi. Okay. The area still maintains, nothing changes. It's a 30, the first one. The second is 12. Okay. And the third is a 4.5 pi. So let's get the products. So 1.29 squared times 30. What do we get? We get a 49.923. And then 923, sure. And then 0.29 squared times 12. What do we get? We get a 1.0092. And then we have 1.21 plus 4 divided by pi squared times 4.5 pi. We have 87. We have 87.1765. Then let's sum them up. Mind you, this one is a negative. Let's not forget, this one here is a negative. Okay, just like this one is a negative. Okay, because this is a hole, a space. So 87.1765 minus 1.0092 plus 49.923. We have a 136. We have a 136.0903. Then the moment of centroidal 62.5 minus 9 plus 10.125 pi. We have 85.3086. Then finally, moment of inertia about the x-axis, x prime, is equal to x centroidal moment of inertia plus y curled prime squared times area, which is equal to 85.3086 plus 136.0903. This gives us 136.0903. This gives us a 221.40 inches to the power 4. Okay, so let's find the moment about the y-axis. Since the centroidal distances along the x direction with respect to the y-axis for each respective area, so we have x scaled 1 is equal to x scaled 2, which is equal to x scaled 3 is equal to 0. Therefore, moment of inertia about the y-axis is just going to be equal to the summation of the centroidal moment of inertia about the y-axis. Okay, so moment of inertia about the y-axis is equal to summation of moments of inertia about the centroidal moment of inertia about the y-axis, which is equal to 90 minus 16. This is minus because it's a whole. It is for this part 2 or area number 2. Then plus 10.125 pi, which is equal to, when we sum up all this area, it gives us a 105.81 inches to the power 4. Okay, so let me use this space here in between to just write down the summary. Okay. So we have we have centroidal distance y bar equal to 3.79 inches. We have moment of inertia about the x prime axis equal to 221. Okay, 221.40 inches to the power 4, and moment of inertia about the y-axis equal to 105.81 inches to the power 4. Okay, so this is finally the summary of the solution. I hope the video was helpful, and if it was, give me a thumbs up, like my video, continue subscribing, sharing my channel. I'll share the other links for the other videos I've done for moment of inertia of an area. Bye bye, and see you in my next screencast.